Welcome, 7th and 8th graders, to today's Physical Science Explainer. We're kicking off Unit 1 looking really closely at forces in interactions. Today we're focusing on mastering the language of motion. Okay, let's dive into this and look at exactly how we measure and, more importantly, communicate motion accurately.
Here's a quick question to get your brain going. How do you know you're moving right now? I mean, you might be sitting perfectly still in your chair watching this explainer, right? But you're also on a planet spinning at about 1,000 miles per hour, orbiting a sun that's just hurtling through the galaxy. The truth is, you can only prove you're moving by comparing yourself to something else. Motion is never an absolute. It's literally always relative to another object. So, to talk about motion like actual scientists, we've got to establish what we call a reference frame. Now, this is an arbitrarily chosen point used to determine the position and direction of an object's motion. And hey, arbitrarily chosen just means we get to pick it. It could be a tree outside, a desk, or a starting line on a track. We pick a 0 point, and then all positions and motions have to be described using that specific reference frame, just so we can share information accurately with everyone else.
But you know, a 0 point really isn't enough on its own. Think about it. If I tell you I moved 5 from the reference frame, that tells you almost nothing. 5 what? Inches? Miles? Light years? Along with our 0 point, we must pick arbitrarily chosen units of size. In science, we typically stick to the metric system, like meters, to accurately measure distance and speed. We basically all have to agree on these units for the data to make any sense.
Now, this is exactly where we get to connect your science skills to your math skills. Once we have our 0 point and our units locked in, we use positive and negative numbers together to describe opposite directions from our reference frame. A positive number might mean we're moving forward, or maybe to the right of our 0 point. A negative number, well, that simply means we're moving in the exact opposite direction, like backward or to the left.
The toy car model. Let's map it out. Now, what's really interesting about this concept is how we can easily take those abstract rules and apply them to a concrete, real-world example right now.
Let's use a toy car in your classroom door as our 0 point. We'll walk through the step-by-step. Step 1, our toy car starts exactly at the classroom door. That is our reference frame, our absolute 0-meter mark. Okay? Step 2, you give the car a push and it rolls forward into the hallway. Because it moved forward from 0, its position is now at positive 3 meters. Make sense? Then, in step 3, the car gets pushed backward. It rolls all the way back, crosses the threshold of the door, and goes into the classroom by 2 meters. Because it crossed our 0 point going in the opposite direction, its position is now negative 2 meters.
And this brilliantly illustrates how scientists interpret motion data using a simple table. Notice the big difference between the position column and the speed column here. Speed tells us purely how fast the car is moving, like 1.5 or 2.5 meters per second. But the position data, that gives us the positive or negative sign, which strictly shows its direction relative to the door. You really need both of those pieces to truly understand the car's whole journey.
Practice time. Level A, Level B, and challenge.
All right, it is time for you to do a little bit of the heavy lifting. I'd strongly encourage you to pause the explainer right after I read this question, test your own understanding, and then hit play. Okay, here's your Level A question. Think about the positive and negative direction rules we just talked about. If the car starts at our reference frame of 0 and moves to a position of positive 4 meters, which direction did it go? Go ahead and pause if you need a second to think it over.
Okay, got it? The answer is, it moved in the positive direction. Whether you personally call that forward, away, or to the right, the positive number describes a specific agreed-upon direction away from our arbitrarily chosen 0 point. Fantastic job if you nailed that one.
Let's step things up a bit to Level B. So, the car is currently sitting at positive 4 meters. It suddenly reverses and travels 6 meters in the opposite direction. What is its new position? Remember to apply that handy math rule for opposite directions on a number line.
The new position is negative 2 meters. Think about it like this. If you're starting at positive 4 and you move 6 meters in the opposite, negative direction, you're going to cross right past that 0 mark at the door and land at negative 2. You're effectively just doing the math problem 4 minus 6.
All right, now for the challenge question. Let's say you change your mind. You decide the door is a totally boring reference frame, so you change your 0 point to the classroom window instead. By choosing a completely different arbitrary reference frame, does the car's actual physical speed change? Think carefully about what a reference frame actually does in the real world. The answer is absolutely not. No way. Only your position numbers will change on your data table simply because you moved the 0 point. The physical interaction, the actual forces acting on the toy car and its physical speed remain exactly the same. The universe doesn't care where we place our 0 point, right? Reference frames are really just a tool we use to communicate data to each other.
So, the crucial point is this. Whenever you're analyzing motion in physical science, always rely on these 4 rules. 1. Choose a reference frame so everyone knows where 0 is. 2. Pick shared units of size so your measurements actually make sense. 3. Use positive and negative signs to clearly indicate opposite directions. And 4. Always remember that speed tells you how fast, while position tells you exactly where.
Parent and guardian briefing. What your student learned today.
Now, I want to take a quick pivot right here. If there are any parents or guardians of our 7th and 8th graders listening, or maybe just watching nearby, I'd love for you to lean in for just a moment. I want to give you a brief look at the core concepts your student just totally conquered today. You see, in this first unit of physical science, the big essential question we're working toward answering is, how can forces explain changes in motion? But honestly, before we can even talk about the invisible forces pushing and pulling on objects, your student first had to master the fundamental language of how we record and describe motion accurately. Today's lesson laid that exact groundwork.
So in short, your student just learned how to interpret motion data using arbitrary reference frames, standard measurement units, and positive and negative numbers to mathematically track direction. These are absolutely critical foundational skills required by the physical science standards, and they'll be using them for the rest of the school year.
I'll leave both students and parents with this final, kind of provocative thought. We now know how to track one toy car moving back and forth, but if forces change motion, what happens to our data and our positive and negative numbers when 2 moving cars physically collide with each other? That question takes us straight into Newton's laws of motion, which we are absolutely going to tackle in our next explainer. Thanks so much for joining me today, and keep questioning the world around you.